Hello everyone, welcome to Teaching Show. In the last video, we had combined our ideal gas equation with the combustion reaction and seen how to handle it. In this video, we are going to combine ideal gas law and use it along with a reaction which is a reversible reaction and it's taking place in a gas phase. Okay, so let's get started. This is the problem I have taken from Felder. It's an unsolved problem and the problem statement is given in the description box. You can go and check it out there. I will explain the problem briefly to you before solving it. Okay, so the reaction which is taking place is NO reacts with oxygen to give you NO2. This is a gas phase reaction. So NO is supplied and oxygen is supplied as air. Okay. Further, that problem says that the volume percent of NO is 20% and air is 80%. Since we have seen in the last video that volume percent and mole percent or volume fraction and mole fraction, they are one and the same thing. So I can directly take these volume fractions as my mole fractions. Okay. So that's how I'm doing, and then they have asked you to calculate what is the final composition of the product gases. Some more information they have given is that conversion of NO is 90%. Initial pressure given is 380 kilopascals, and you have to also find out what is the final pressure of the product gases. Okay, so let's get started. First of all, I will have to choose a basis. Since I know the mole fractions of the inlet stream, so I am going to choose my basis as 100 moles of feed. Okay, based on this, I am going to first calculate what are the inlet amounts which I am putting in the batch reactor. So initially NO which is put into the batch reactor is 20%. So 20% of 100 is 20 moles. Remaining is air. So that is what nitrogen is 79% of air. So 79% of 80, that is 63.2 moles. Similarly, oxygen is 21% of 80, that is 16.8 moles. So inlet, I know how much I am putting into the batch reactor. Okay, I have to find out outlet composition. I have chosen a basis already. I have already prepared a fully labeled flowchart. So let's start the problem. The third step which has always been there was to calculate first the degree of freedom. I am going to use atomic species balance for this problem because it involves a reaction. So I am going to first do degree of freedom analysis for atomic species balance. How many unknowns do I have? 1, 2, 3 and 4. So I have 4 unknowns. Further, there is one more unknown which is PF, that is the final pressure which I have to find. So how many unknowns do I have? I have 5 unknowns. Atomic species balance, how many of them are there? Nitrogen and oxygen, there are only 2 atomic species. So atomic species balance is 2. Inert balance is 1, that is nitrogen. Okay, because it's not taking part in the reaction. So nitrogen I am going to treat as inert. Okay, so keep in mind this is my inert. Okay. Process specification, one is given 90% conversion of NO. Degree of freedom turns out to be 1, but it is not the case. I have one more thing, and what do I have? I have my ideal gas law. So this is one more equation which I can use. So I have ideal gas equation which I will use to find out this final pressure. Okay, so this is one more equation and my degree of freedom is then 0. So this problem is solvable. I can solve this problem. Okay, so let's do that first. Whenever I solve such type of problems, I ask you to first make use of your process specification. And what is that? Conversion of NO is 90%. Okay, so how much is unconverted? Conversion is 0.9. Unconverted fraction is 1 minus 0.9, that is 0.1. So I have the amount of NO which is unconverted, that is equal to 0.1 times what is going in, and that is 20. So directly I get 2 moles. Okay. So N1 I have calculated using the process specification. Next, I told you after process specification what you are going to do. take inert balance. Nitrogen is not taking part in the reaction, so whatever is going in should be coming out. So in is equal to out, and my N2 is equal to 63.2 moles. Okay. Next, we are going to make use of atomic species balance. So first I will take nitrogen balance. Okay. So I am taking N balance. How much N is going in? 20 moles. That is equal to, mind it, I am treating nitrogen as inert, so you are not going to do 2 into 63.2 times and add it over here, because I am considering this as my inert species. So don't include this nitrogen in your nitrogen balance. This has already been taken in your inert balance. Okay, so I will write inert balance. So for nitrogen balance you have to take only what species? NO and NO2. Okay, so how much N is going in? That is 20 moles of N is going in. How much is coming out? That is N1 plus N4. N1 I have already calculated, it is 2 moles. 2 plus N4. So that implies my N4 is equal to 18 moles. So I have got my value of N4 as 18 moles. N1 is 2 moles. N2 is 63.2 moles. Okay. The only thing which is remaining is now I have to take oxygen balance. So I am taking O balance. How much O is going in? O is going along with nitrogen oxide, NO. So that is, in is 20 plus 2 times of 16.8. So 2 times 16.8. And that should be equal to the oxygen which is coming out. It is coming out in the form of NO, that is 2 moles, plus with oxygen, so this is 2 times N3 plus 2 times N4. Okay, now N3 I don't know, but N4 I know. N4 is 18 moles, so it is 2 into 18. This is simply one equation in one unknown, and I am going to calculate that. If you do that calculation, what you get is your N3 is equal to 7.8 moles. So I have calculated the composition. Okay, composition means, okay, these many moles are coming out. What you can do is you can easily convert it into mole fraction. That I will leave for you to do it on your own, but we will proceed to finding out what is the final pressure. Okay, so final pressure that we will be finding out using our ideal gas law. What is ideal gas law? PV is equal to nRT. Okay, I told you whenever you have ideal gas going in and coming out, okay, do not try to figure out what is volume, what is all these things. I will take a ratio of outlet to inlet. Okay, so if I say that my outlet is marked by, see, I will give the subscript F to the final case, and I will give my subscript I to initial case. Okay, so PI that is equal to NI TI. Fine. And I can also write PF VF is equal to NF RTF. Since in the problem statement it is given that this is an isothermal reactor, so temperature is not changing. Okay, so I don't have two different temperatures, they are the same. Since it is a batch reactor of which your volume is fixed, so you do not have two volumes. Okay, the volume remains the same. Fine. So the only thing which is varying is that number of moles and your pressure. Okay, initial number of moles Ni I know, final number of moles also I know if you just add them up. So if you add these all number of moles, the total number of moles, they come out to be 91, and this is equal to NF. Okay, I will just erase this so that you don't get confused. So I know final number of moles, I know initial number of moles, I know what is the final pressure. I have to just I know the initial pressure, I have to just calculate my final pressure. So do that, divide one equation by the other. So PF by PI, that is equal to NF upon NI, or that implies that your final pressure, that is equal to NF by NI, NF is 91 divided by NI is 100 into your initial pressure is 380. Okay, so your final pressure then is 345.8 kilopascals. Okay, so first part of the problem we are done. In the first part of the problem, we were asked to calculate what was the final pressure. Now, second part of the problem, it gives you the final pressure and it asks you to calculate what will be the equilibrium constant, because this is a reversible reaction. So, there will be a equilibrium constant. Okay. So, final pressure is given. You have been asked to calculate equilibrium constant using this equation. This equation we have already seen in terms of mole fractions in one of my previous videos on reversible reactions. Okay. So, this is not a new equation for you. Since for this pressure I don't know how much is the conversion, okay, so that process specification is gone. Okay, remaining things are same. I have the same basis, the inlet is conditions are the same, so this condition is the same, 100 moles I am choosing as basis, and I have calculated what is the inlet amounts of all the reactants and the inert. Okay, now for this part B, I will use extent of reaction to solve this problem. Let's say extent of reaction is epsilon. Okay. First of all, we will calculate our degree of freedom. How many unknowns do I have? I have N1, N2, N3, N4 and K. So, number of unknowns are 5. How many reactions I have? So, number of reaction 1. So, I should have 6 equations in all. Okay. Let's count them one by one. How many reacting species do I have? Reacting species equal to 1, 2 and 3. So, 3 reacting species. So, I can write 3 equations in terms of extent of reaction. I have one inert balance. Okay. 3 plus 1, 4. I have one equation for K. So, equation for K, that counts as 1. Okay. And one more thing I have, and that is, see, my final pressure is given. From final pressure I can find out my total number of moles. Okay. Or which I can use along with this equation. So, how am I going to find my total number of moles? Using this, I will have to use my ideal gas law. So, somewhere my ideal gas equation is one more equation which I can use. Okay. So, then my degree of freedom is equal to 0 and I can solve this problem. Let's see how your ideal gas equation now comes into picture. Okay. So, we will start by taking first of all my process specification first. Okay. Let's see. So, my process specification is what? I have PF is equal to 360 kilopascals. In part A, we had seen that I can write ideal gas law for the final state as well as the initial state. Volume remains the same. Isothermal batch reactor temperature remains the same. So, finally, I get an equation which is only in the total number of moles and the initial and final pressure. Okay. So, same equation, I am just taking the ratio of the equation written for the final state divided by the equation which is written for the initial state ideal gas law. So, I am going to write P, F, V, NF, R, T, and this should be divided by Pi, V, Ni, RT. Okay. Now, I don't know what are the final number of moles. Remaining things I know. So, NF I can calculate from this process specification using ideal gas law, and that is equal to 100 into 360 by 380. Okay. So, my final number of moles are 94.73. Okay. This I will write down somewhere. Fine. So, I will just write down my NF is equal to 94.73 moles. So, after making use of one process specification, that is your pressure, final pressure is 360 kilopascals. Using my ideal gas law, I have calculated what will be my final number of moles. Okay. Then I am going to use my inert balance. I will not write it. Inert balance, in is equal to out. In is 63.2 moles. So out should also be equal to 63.2 moles. Okay. Then now I am going to make use of my reacting species and write an equation each in terms of extent of reaction epsilon. Okay. So final number of moles N1, that should be equal to initial number of moles, that is 20, minus epsilon. N2, that's an inert, so no need. N3, that is equal to initially N30 is 16.8 minus 1 by 2 times epsilon. N4 is equal to initially no NO2 is present in the feed, so 0 plus epsilon, so only epsilon. Okay. So I have written these three equations. Also I have N2, that is equal to 63.2 moles. Fine. If I add N1, N2, N3, N4, that is equal to my final number of moles. So let's add all these four equations. Okay. So I have N1 plus N2 plus N3 plus N4, that is equal to 63.2 plus 20 plus 16.8, that is 100, minus plus epsilon cancels out, so minus half E. Okay, so I have added all these four equations to give me my final number of moles, but this I know is equal to 94.73. Solving it for epsilon value, I get the value as 10.54 moles. If I put the value over here, I get N1, that is equal to 20 minus 10.54, that is 9.46 moles. Okay, N3 is 16.8 minus half E, so that is equal to 11.53 moles. And this is 10.54 moles. Okay, so I have calculated now the molar composition of the outlet stream. Fine. So let me write all these over here. Shall I write it? Yeah. So this is 9.46, this is 11.53, and this is 10.54. Okay. Now we will quickly calculate whatever is required. I have to calculate my partial pressure because this equation is in partial pressure. Okay, so I'm going to write down species. I require the partial pressures of only NO2, NO and O2. So I will write down only these species, NO2, NO and O2. What are the number of moles of these? Number of moles here are 9.46, 11.53, 10.54. Total number of moles I know, so I can find out mole fraction of these. Okay, I have to find out mole fraction in order to calculate my partial pressures. Okay, so I need to know my Y values. So Y is given by 9.46 divided by the total number of moles, and that comes out to be 94.73. So I am doing that, 9.46 divided by 94.73, and I get the value approximately at 0.1, 0.122 and 0.111. Okay, so these are my mole fractions. One more component is there, but that is not required, so I am not going to do the calculation for that. Once I get the mole fraction, I know my partial pressures are Y times total pressure, that is 360 kilopascals. So 0.1 times 360, that gives me 36. So 36 kilopascals is the partial pressure of NO2. Similarly, I calculate my partial pressures 43.92 and 39.96. These are in kilopascals, but in the problem statement they asked you to calculate your K value in units of atmosphere. So I am going to convert this partial pressure into atmosphere. I know the conversion factor 1 atmosphere, that is equal to 101.325 kilopascals. Okay, so making use of that, I am going to convert it into atmosphere. So this is 0.355 atmosphere, this is 0.433, and this is 0.394. These are just calculations. Okay, so now I have partial pressure PNO2, PNO and PO2. Okay, put this in this equation and find the value of K, which comes out to be 1.68, and its units are atmosphere raised to minus 0.5. So this is your problem which is done. I have calculated my K value. So in this problem what we had done was that in part A as well as in part B, while calculating the number of equations I have also included directly or indirectly my ideal gas law, counted it as one equation because it was used to find out one variable. Okay, so that is how I just take care of my calculations and make the degree of freedom equal to 0 by counting ideal gas law as one of the equations. Okay, so I hope you understood how to solve such type of problems, and if you like this video, please don't forget to subscribe to my channel, like the video, share the video, and thanks a lot for watching. Thank you so much.